This is part 1 of our introduction to spectroscopy or spectrometry. These three terms are often confused. Spectroscopy refers to the interactions of electromagnetic radiation with matter, so it's a general term. Spectrometry or spectrophotometry is used when we're going to measure the absorbance or emission of radiation. Exactly how the radiation interacts with matter is directly dependent on the energy of the radiation. Let's talk about molecular quantum effects. And this is a quantum function. As electrons and atoms change energy levels in discrete increments, going from energy level 1 to 2 to 3 to 4, or 3 to 2, or 4 to 5, so do electrons and whole atoms and molecules. This can be done by rotation, vibration stretching, and vibration around bond angles. We'll show you in animation. This shows you stretching along a covalent bond, say in the hydrogen molecule. This shows in the water molecule how there can be an angular component to the vibrations that we see. And in a water molecule, again, you can see stretching here that can either be in or out of phase between the hydrogen and the oxygen atoms. Let's talk about the interaction. The higher energy ultraviolet and visible wavelengths are going to change the energies of valence electrons. We saw that in studying the atomic structure. Infrared radiation, however, is absorbed by molecules, and we're going to either stretch the bonds, like you saw in the animation, or we can actually rotate the whole molecule around one or more axes, and the infrared radiation does that. Radio waves are used in nuclear magnetic resonance studies, and they're going to affect the spin of nuclei in a magnetic field. It can actually turn the nucleus upside down and make it spin in the opposite direction. And of course, that also would be a quantum effect. This is the electromagnetic spectrum to give you an idea of what we're talking about. X-rays are typically used to study crystal structure. This is where Dr. Pauling first made his impact in chemistry. The UV-Vis spectrum, we're studying the energy level changes of valence electrons in and out of chemical bonds. Infrared is going to make the covalent bonds stretch and bend, and it will make molecules rotate at, if we absorb IR, then molecule can actually rotate at a higher frequency. And then radio waves are used in combination with very, very strong magnetic fields to flip the light nuclei of molecules. Let's talk about the particle nature of radiation. We know that electromagnetic radiation also has the properties of particles, and the energy of the particle would be equal to Planck's constant times the frequency. Molecules exist in a certain number of possible states, corresponding to definite amounts of energy, eigenvalues. The molecules can absorb energy, and if it's the right amount of energy, they can change to a higher stretch state, vibrational state, or rotational energy level, and we would call that the excited state, just as we do when we're studying changes in the atom and the electrons around the atom. The amount of energy absorbed in transitions between these energy levels is exactly equal to the energy difference between the states. So again, just as in the atomic structure, so also in the molecular structure, not just any energy will be absorbed. only the specific energies that make the molecules change to a higher energy state. You may recall seeing the emission spectrum of sodium. Here we have the absorption spectrum. Here we have the emission spectrum of sodium. The 330 nanometer line is in the UV, so our eyes can't see that particular line. Now, for a simple molecule, we can talk about the ground state, the first energy level, and the second. If, say, there's an excited state in the molecule in E2, if it relaxes to the ground state, it can go to a different vibrational energy state, and some sort of wavelength will be emitted. That's typically going to happen in the UV or IR. If you send the right frequency, the right energy, into a ground state molecule, you can excite it, just like this. Now, the vibrational energy levels are closer together, and that means it would be a higher or a lower energy change. Obviously a lower energy change. And so now we're looking at not the ultraviolet, but perhaps the visible or infrared. Let's define the wave number. You're familiar with identifying a spectral line with its wavelength, and you calculate the frequency by the formula. Frequency equals the speed of light divided by the wavelength. Physical scientists frequently identify the absorbance lines or peaks of a spectrum with something called the wave number. The wave number is not the wavelength. The wave number is defined, this is the Greek letter nu, with a little squiggle over it, with that tilde over it. It's equal to the reciprocal of the wavelength. That's what the wave number is defined as. And you're going to see spectra with wave numbers on them. We will continue in the next video with specific kinds of energies. And we'll see what types of changes they're associated with.